Trigonometry is the study of the relationship between angles and sides and triangles. Look, up until this point, unless you've actually done some work with trigonometry, the way that you've looked at angles and side lengths within triangles has actually been separate. It may have seemed like you were working on them at the same time, but you really weren't. As far as angles, the extent of what you may have done with that is the Triangle Sum Theorem, which is that the three angles in any triangle are going to add up to 180 degrees. So given two of them, you could figure out what the third was. Then as far as side lengths, what you've probably used a lot is Pythagorean Theorem. If you're given a right triangle, and this is a picture right triangle, if you didn't notice the title that we have here, Solving Right Triangles. If you have a right triangle, you can do Pythagorean Theorem. Given two sides, you can find the third one. But you haven't actually mixed those two concepts together yet, and that's what trigonometry is about. As the title would suggest here, we're going to start with right triangles. Okay, so I have a picture of a right triangle. This, of course, is going to be the right angle. Okay, so I'm going to go ahead and add a little box in there to show that it is perpendicular at that spot. You've got the 90-degree angle. And in a moment, I'm going to introduce this symbol, which is the symbol theta. It's a Greek letter, and theta is a common letter that we use to represent an unknown variable or an unknown angle that we have. So instead of calling maybe angles x and y and stuff like that, which we'll sometimes do, a lot of the time what we'll do is use theta as our variable, and theta is spelled Theta. Okay. All right, so we're going to introduce that in just a second, but before I do that, we're going to have three sides that are here. Okay, there's three sides to a triangle, and they're going to be given names: hypotenuse, opposite, and adjacent. And I'm going to start with hypotenuse because the hypotenuse is based off of where we see the right angle. The hypotenuse is always going to be the side that's across from it. It's also always going to be the longest side, and you can also describe it as being the diagonal side that we have. So I'm going to go ahead and label that hypotenuse. Okay, so that one is the hypotenuse, and it has nothing to do with theta. It's all about being across from the right angle. Now, theta is going to be one of the two acute angles, and it doesn't really matter which one you choose it to be. You actually get to choose where your theta is. It doesn't matter if this is theta or if this is theta, but depending on which of those you choose to be theta, the other side's opposite and adjacent will be determined. All right, now a little side note about the two angles that we have here that are acute, because this will come up a little bit later. Remember that a triangle does add up to 180 degrees. So if this is 90 degrees and you take that from the 180, that leaves you 90 degrees, which is going to get split between these two angles. So the two acute angles that we have here, they are going to be complements of each other. They're always going to add up to 90. Okay, and again, that's going to come up a little bit later in things here, and it's a good rule just to be aware of. All right, let's go ahead and just choose this angle to be theta. Now, if I choose that one to be theta, the other names that I have for the legs of the triangle, the opposite and the adjacent, will be determined. The opposite is going to be the side that is opposite of where that angle is located, so it's all the way across the figure to here. Okay, so in this picture, it's going to be the height. All right, that is the opposite. Adjacent means next to. Okay, in math, I usually like to describe the word adjacent as next to and in contact with. Okay, so the definition is that it's next to, but I like to say in contact with because I think that helps emphasize like where you'll find things to be adjacent. Okay, so this is going to be the adjacent side because it is right next to that angle. It's in contact with it. It's making that angle. Okay, so that's the adjacent side there. Now, if we choose theta to be up at the top, okay, if you chose theta to be here, the hypotenuse is still the hypotenuse, but that's going to make the base the opposite side, and it's going to make the height the adjacent side. So the choice of where theta is going to determine where these are at. Now that we have our figure all labeled, we can talk about the three basic trigonometric ratios. Recall that in mathematics, a ratio is usually presented as a fraction. There are three different ways that you can write fractions, but the only one that is useful for mathematics is to present this as a fraction, so that's what we'll be doing next to each of these. All right, so we have three basic trigonometric functions. We actually have a total of 6. which you'll see the other three a little bit later, but not in this video, but you'll see it later on. These are the three basic ones that you'll see. These are sine, which is actually spelled S-I-N-E, but is abbreviated here. So don't read this as sin. This is actually sine. There would be an E at the end of it, but we just cut it off at 3 letters. This is cosine. Okay, so C-O-S-I-N-E. That is cosine, and we abbreviate here. Do not read that as cos. The third one is tangent. It's spelled T-A-N-G-E-N-T, tangent, which we abbreviate as T-A-N. And again, don't read that one as tan. This is going to be tangent. So it's sine, cosine, and tangent, not sin, cos, and tan. Don't read them that way. All right, now each of these are we call them ratios here, but later we're going to really refer to them as functions as well. Okay, so I might bounce back and forth between talking about them as ratios and then also talking about these as functions. If I take the sine of theta, I'm going to get back a ratio, which is a comparison of two numbers. If I take the cosine of theta, I'm going to get back a comparison of two numbers, which is also going to be fraction, and the same thing for tangent. Now, what the sine of theta is going to give us back is a comparison of the opposite side to the hypotenuse. So again, as a ratio, I'm going to have a fraction. The top is going to be the length of the opposite side, and the bottom is going to be the length of the hypotenuse. It's a comparison of those two things. Cosine is going to be a comparison of the adjacent side to the hypotenuse. That's the adjacent over the hypotenuse. And last, the tangent is going to be a comparison of the opposite to the adjacent. Okay, and that's going to be opposite over adjacent. And these are things that you will want to have memorized. These are also the foundations to what we're doing in trigonometry, so it's important that we have all this organized in our brains. In example number 1, what we're going to do is verify that these ratios are actually true. That is, that if I went to the calculator and I typed in the sine of an angle measurement, like a real angle measurement, and we're going to use a protractor to figure out what it is. If we did that, it will give us the comparison of the two sides that we would have in our ratio. Okay, so this is all for verification purposes and for you to buy into the fact that this stuff is real. All right, what we have for our right triangle here, let me go ahead and add the right angle in there. What we have for a right triangle is a 5, 12, 13. Okay, and these are all measured in centimeters. I went with those numbers because these are what we call a Pythagorean triple. There's a lot of Pythagorean triples out there, but most of them are larger numbers. This one works out really good. If you take 5 squared plus 12 squared, it does in fact give you 13 squared. And you can test that out to the side if you didn't know that that was a triple. But it is, and it'll make things much easier for the example versus me giving you some just sort of wacky decimal numbers that would be on there. All right, so what I'm going to do first is just measure to verify that these are the right measurements. All right, so we can see there on the base that you've got 12 centimeters. The height is going to be 5 centimeters, and this one's barely going to fit on my little ruler here, but we've got 13 centimeters there. Okay, so we have a 5, we have a 12, and we have a 13. It's also kind of useful just to check that out with Pythagorean Theorem and see that it actually does work, right? And it's a way to test out Pythagorean Theorem and start to verify, wow, that actually does make sense. The numbers turn out right, and if you measure them, they match up to that set. All right, next, what we're going to do is choose an angle to be theta, and I'm going to go ahead and let theta be here because I think it'll be easier to look at when I start measuring it with a protractor versus attempting to measure over there. For that, I would probably just rotate the paper around. Okay, so I'm going to choose this one to be our theta. And if I choose that to be theta, that means that this side over here is the opposite. Of course, across from the right angle is your hypotenuse, and this will also be your adjacent side here. Measuring our angle. All right, let's put the protractor on here. All right, what I'm going to attempt to do here is I'm going to measure on the outside perimeter because I got somewhat of a thick line here, right? So depending on where you measure around that line, if you measure maybe in the inside part of it, or the middle or the outside, well, you don't get different answers, but you want to know what you're doing so you can be as accurate as you can. So I'm going to attempt to measure on the outside of these thick black lines here. And let's see, from 0, you got 10, you got 20, you get a little bit more. And if I'm going to the outside part, that looks like it's about 23 degrees. Okay, about 23 degrees. Now remember that in a protractor, you're going to be limited to the accuracy of how you can measure things, because at the best you can get to a degree measurement, but whether it's like a half, like maybe 22.5 or 23.5, that would be hard to see in a protractor. All right, so let's verify some things here. The sine of theta should be the opposite over the hypotenuse. Okay, so what I'm going to do is type in the sine of 23 degrees. I'm going to type that into my calculator, and then I'm going to make a comparison to the opposite and the hypotenuse. So let's type this part in there first. All right, now you may be using a different type of calculator. I'm not really sure what you have, but the trig buttons are pretty much available on all calculators, even like a $5 scientific calculator. You'll see these things. So on the calculator that I have, the right here on the front, there's sine, we got cosine, we got tangent. Now before I use those buttons, I do have to make sure that I'm in the right setting. So there's two different settings. There's radians and there's also degrees. Radians is actually the true way to be measuring angles, and we'll see about that stuff in a video coming up a little bit later. But we're doing things in degrees today. All right, so if you look at the top of my screen here, it actually says the word radian. So some calculators might write rad, or they might have something up there, but somehow you want to make sure you're checking the right stuff here. My calculator, if I go to the mode, which is right here next to the blue button, if I go to the mode, I can scroll down to where it's radians, and then I can select degrees. You're going to see a change up at the top. That means that we're in the right setting, and then I'll get out of this by pressing second mode, which is actually quit. Okay, so I can always look just at the top of my screen here to see what I'm in, and whatever calculator you're using, just get comfortable with being able to know what setting you're in. All right, so let's put that back over here because I got to type some stuff in. All right, let me type in the sine of 23. Now that I'm in degrees. All right, it's going to come back with this long decimal number we have here, which is 0.39. And you got a lot more to follow after that. I'm going to go ahead and take, let's go with 4 digits here. So that's going to be 0.3907. All right, so it's not exactly that number, but it's really approximate, but I just wrote the equal sign. While I'm here, let me just go ahead and type in the other ones, just so that I have all those numbers. All right, so cosine of 23, it's going to give me that, and then tangent of 23 is going to give me that number. So what do these numbers actually mean? Okay, we took the sine of 23 and we got this decimal number. We took the cosine of 23 and we got that. We take the tangent, we got this number. What do they really mean? Well, if we go back to the definitions, the sine of theta is the opposite divided by the hypotenuse. So what that means is that this number should be the opposite side 5 divided by the hypotenuse 13. If we divide 5 by 13, we should get that number. Okay, so I'm going to take 5 divided by 13, and I get this, which does look a little bit different, right? Ours is 0.3907. This is 0.3846. Okay, so it does look like we're off by a good amount here, but it really isn't. Okay, they both have the 3. It looks like you might be off by 1 when you get to the second place, but that would have been like 1/100th that you're off by. Of course, if you look at the next decimal, use that one to do a comparison. It looks like it might only be a difference of about 6 thousandths, but then you see it carry over into the next digit. So they are really, really close to each other. Now, the reason that they're not exactly the same is because when we use our protractor to measure the 23 degrees, that involves a little bit of rounding and decision making, because the true angle that goes with the 5, 12, 13 is not going to have angle measurements that are whole values. They're actually going to be decimal numbers. So that's where the actual variance is in there. All right, well, let's go ahead and check out the other ones though. The cosine of 23 should be equal to the adjacent divided by the hypotenuse. The adjacent in this case was the 12, so 12 divided by 13 is going to give you 0.923. All right, again, pretty darn close to that. It's off by like 3 thousandths. Pretty close there. All right, and then if we do the tangent of 23, that's not what I want to do. I already had that typed in. What we want to do is verify that that's the right number, which is the opposite divided by the adjacent. So that's going to be 5 divided by 12, which give you 0.41 and a bunch of repeating sixes. So that 6 would be enough to round it up to a 4 or 2. So at least you see some comparison. But again, they're going to be pretty close to the answers. It's just we're limited in how we can measure those angles there. In example number 2, we're going to take the information that we just figured out and apply it to solving a problem, to actually figuring out things that we don't know. Okay, so we're not just going to be evaluating things and seeing that the definitions work, but we're going to be using those definitions to find things that we otherwise would not be able to. The instructions say that we're going to be solving the right triangle. Now, what that means is that you have to figure out everything that you don't know. Okay, now a triangle is going to have 6 parts. It's going to have 6 total parts. It's going to have 3 angles. It's also going to have 3 sides. Okay, in our picture, you've got 3 of them provided for you, and that's always going to be the case. If you've got 3 pieces of information, you can get the rest of it. So the things that we do know, we know that we have a right angle. That's 90 degrees. So that's important. You know that you got an angle over here of 66 degrees, and you know that the hypotenuse is a 50. There, we got 50 length there. All right, things that we don't know the other angle that's here, but that one's pretty easy because these two are just complements in a right triangle. Okay, so the first answer we can go ahead and just take care of here. Angle B is going to be the complement to 66, which means that it is 24. It's going to be 24 degrees. Side lengths, that's going to be the more challenging part here. You've got the hypotenuse, but you don't have either leg, so you can't apply Pythagorean theorem here. What we're going to do is use the trigonometry. All right, now to start it off, we need to choose one of the angles to be our theta. Since the 66 was what was printed here, I'll just let that be theta. Okay, so I'm going to call the 66 degrees theta. Now, if 66 degrees is the theta, then the other sides can be identified. We already know this is the hypotenuse, but the side across from the 66, that will be your opposite side. The side next to it's going to be the adjacent. So you get those names. Now, if I had gone with 24 as my theta, these would be different. Okay, but I'm identifying 66 as my theta, which means that I got the names for those two. Now, I'm interested, let's say that we're interested in figuring out A first. We'll go ahead and get that side. If I want to get A, that means I need to choose a trig ratio that involves the opposite side. In addition, the other side that I have available is the 50. I have that one. I don't have the adjacent side. Okay, so I want to think about what trig function related the opposite to the hypotenuse. And that trig function was sine. So if I take the sine of 66 degrees, that would be equal to the opposite divided by the hypotenuse, which would be A divided by 50. And now this is an equation that I can solve. And if you've never done one of these before, it might be a little bit intimidating, but what you need to understand here is that this is just a number. That's all it is. It's going to be a decimal number, but it's something you type into the calculator and you just get a number back from there. So if you think of this as one whole item, it just represents a number, and that's equal to A divided by 50. We can just really concentrate on, well, how do you get A by itself? How do you undo the 50 that's next to it? And for that, you would multiply by 50. All right, so if you divide A by 50 and then multiply by 50, those essentially cancel out. They undo each other. But then to balance the equation, you're going to multiply the 50. I'll put a little dot there for multiplication. You're going to multiply the other side by 50. And you can actually go straight to the calculator with that. All right, so I'm going to take 50, and then you don't even have to type the times button. You can skip over that. It'll understand. You can just type sine, type the angle that we've got, go ahead and press enter, and that's the answer. You get 45.68. We'll go 2 decimals here. Okay, so A is equal to 45.68. The reason I'm going to take so doing maybe 1 decimal might be fine, but I'm going to take 2 of them because at the end I want to verify with Pythagorean Theorem that these look like good answers. Okay, so now with that, you do have the option that you could do Pythagorean Theorem with that leg and this hypotenuse to get side B. So that is an option, but I'm going to use that to actually test my answer. What I'm going to do here is set up another trig problem so that we can actually solve for B. Okay, so let's say we're solving for B. You've got the 50 and your theta is 66. We're looking for the trig ratio that is going to compare the adjacent to the hypotenuse. That would be the cosine. So if we took the cosine of 66 degrees, that would be equal to the adjacent side B divided by the hypotenuse 50. And you'll notice here that the equation really doesn't look much different than the one we had right before. And that's true. There's going to be a lot of repetition how the problems look when you're setting up, and even how you're going to end up solving them. So for this, we're also just going to multiply by 50 both sides here. So if you want, you could just skip ahead here, go straight to the calculator, right? Go straight to the calculator with 50 cosine 66. So pull that up. So you got 50, we'll press cosine 66. Press enter, and that is going to give us 23.34. We'll go with that. And that's your other side. All right, and now, just to verify things here, I'm going to do some Pythagorean theorem. In fact, I'm not even going to round these off. I just decided that here. Okay, so Pythagorean theorem says we're going to do a squared plus b squared and should equal 50 squared. So I'm actually just going to recall these other answers. I'm going to take that answer and square that one plus this answer squared. Okay, so that's a squared plus b squared, and it gives me that number, which turns out to be a really nice looking number, right? Because all it is 50 squared. So these answers are right. Okay, those are the right leg lengths that we have for that picture. When using the trig ratios to solve problems, there's actually 3 different types of solving problems that you come across. The first is where you're solving for the numerator, which is what we did in example number 2. The second is where we're solving for the denominator. Okay. The third is where you're going to be solving for an angle itself, which is what we're going to do in example 3. So solving for the denominator, I don't have in the video, but use your algebra skills and you should be able to figure out how to get that answer. All right, so for an example number 3, the highest tower in the world is in Toronto, Canada, and it is 553 meters high. An observer 100 meters from the center of the tower's base sights the top of the tower. Find the angle of elevation. All right, so really what we have here is just a picture of a right triangle with some story that goes around it. You've got the tower, which is one of the legs of the right triangle, that has a length of 553 meters. Then on the base of the triangle, you're going to have the distance that the observer is from this, which is 100 meters. All right, now they did say that he's 100 meters from the, from the center of the tower's base. That way, if you measure right to the middle of it, you would get a true perpendicular up to that top part there. So that's why that's mentioned. But ultimately what we have here is, it is a right triangle, so there's your perpendicular. You have a right triangle that has leg lengths of 100 and 553. What we're asked to do is figure out this angle. So we're really trying to figure out what is theta in our problem. Theta in this case will be the A value. All right, with respect to where that angle is, this side is called the opposite. This side is called the adjacent, and this would be the hypotenuse, which the hypotenuse is not provided for us, and we're not even interested in figuring out what it is. So we're going to take a look at our trig ratios and see which one we would use. Remember, we do not want the hypotenuse. It doesn't help us in any way here. So if I look at the choices that we have here, it's not going to be sine because that needs the hypotenuse. It's not going to be cosine because that involves the hypotenuse. It's going to be the tangent, the opposite in the adjacent comparison. So here's what our equation looks like. We're going to take the tangent. I was referring to it as theta here, but in the picture it's a. So I'm going to go ahead and write a this time. The tangent of a should be equal to the opposite, 553, divided by the adjacent, which is 100. The tangent of a is equal to 553 over 100. All right, now that's something I can evaluate, right? I can just type it in. In fact, if you divide by 100, it just moves the decimal 2 spots back. Okay, so this is just a number. You actually don't even have to divide it. I don't want to go through that because most cases when you divide them, you'll get really weird numbers like the 5s and the 12 and stuff like that. All right, so really what we're looking at is how do we get the tangent away from the a? Okay, so now we start thinking of the sine, the cosine, and the tangent as functions. And if we do think of these as functions, then every function has an inverse that goes along with it. You have a function that can be used to undo whatever's happening here. And on the calculator, those inverses are going to be found by typing the second button, and then, let's say we're looking at tangent. You type the second button, you'll see the little arrow up there now. And if I type tangent, I'm going to get that. So it may be different depending on the calculator that you're using to find it, but you're looking for stuff that has the trig functions with a -1 next to it. Okay, and that means the inverse function. Okay, and if I press second sine, second cosine, I get the inverses for those as well. Okay, so here's how it would look. Now you don't have to do all the work that I'm going to demonstrate here, because this is a bit longer than it actually needs to be, but I want to at least give one description of like what we're actually doing here. We're going to take both sides of the equation and put them into the inverse tangent, also called the arc tangent. Okay, so you can read this as inverse tangent, or you can read it as the arc tangent. You can read it that way. That would actually be one word there. Looks a little bit spaced out. Okay, but we're going to take both of these and put them in the inverse. So we got tan A here, got the 553 over 100 there. And this inverse is going to undo what tangent is done. So if we took the tangent of A and then we undo the tangent, we just get A. So almost as a summary, because you don't really need to write all that stuff, as a summary, to figure out an angle, what you really need to do is just take the inverse tangent of the ratio, and that will give you the answer. You don't really have to do all the extra work that I showed there. Okay, so I'm going to take the arc tangent, or inverse tangent, 553 divided by 100, and that is it. Your angle is going to be 79.7 degrees.
Wait, what?